So first, I do this lecture on first today. I would like to give you equation and also how to drive the equation. So then so x is a position vector. The position vectors and t is a time value. And I only consider the no isothermal case. Consider only the isothermal case. Maybe in Japanese. Therefore, we don't have any energy equation. We don't have. Which is complicated, but maybe later, if I have a time, then I would like to talk about also non-thermal, no isothermal case. But that case is the energy equations play an important role. Anyway, first, for simplicity, I consider only thermal equation, no isothermal. So isothermal. Therefore, I consider velocity field. T is transpose. This vector, and so this is a vector velocity. Txt. Xt is a these three unknowns are unknown to describe the motion of viscous fluid. I only consider the viscous fluid. I don't give any reason why I consider only the viscous fluid. Because okay. Anyway, then we know that the equation is first equation is not t plus g u. This is a equation momentum, equation of mass, the conservation of mass. And then rho dt is equal to s so that I give this equals to divergence. this is conservation of momentum. So to treat the viscous fluid, usually we use these two equations. So of course, isothermal test, then conservation of mass and conservation of momentum. So this is we now call the Navier-Stokes equations. Then later, I consider maybe this year mainly consider this incompressible case, but also maybe my technique is also applicable to the compressible case. So maybe I also want to talk about compressible case. Anyway, equations to describe the viscous fluid is these two equations, the Stokes equation. Okay, then today I plan to give how to derive these equations. But anyway, this is a representation by using the vector, and this is L by L. Sorry, matrix. And this is so. Okay. So it is in this is L by L matrix, and this is L vector. So maybe I should give some notation. So as you know, that the div divergence B is dj here over dx is a vector of function. This is divergence. And the rho t is a time derivative of rho. Rho is a scalar. And dt u plus u nabla u dot nabla u. This equation is a so-called material derivative of a velocity field. But later I will give you how to derive it. But so far it's just an explanation of this notation. It's nabla u usually. So it's okay. It's an N vector, and the number f is also, if f is a scalar, then the number f is N vector, so it is just in a product. And then, yes, it's here is. So S is matrix now, N by N matrix. And my notation if S is divergence S is an n by n matrix. So this is this one, two. Si is a raw vector. Maybe easy to understand that this notation. So this is the usual vector. So this one, two. This is one. And each component, this part is a vector. You understand this notation. Therefore, DBF, so if I use this chapter B, this case is a divergence. We take this way. So you have the inner vectors. Therefore, by using this notation, so component-wise, you can write component-wise. So first equation is dt dj k. And the second equation is dtui. As component of equation is ui is equal to s and j plus this is a component-wise description of system equation, obviously equations. So this is if we hear this lecture first time, then maybe the notations are very much complicated. No problem. This equation long time, therefore no problem. But the description is rather complicated. So because of the equation gives the vectors, not the scalar. But this is an important point because question of vector is quite difficult to solve. You cannot take any maximal principle or something. But on the other hand, the equation given by vector is a very natural because usually we have the cosmos is a 3-dimensional. So in every direction we have a different motions. Therefore, okay, but then how to solve? So how to derive the equation? Maybe we have to consider some of the Lagrange ideas. So to describe the motion, so I use to describe the motion. Usually we use the map IT, Y is map to Y. It's n vector, so phi 1 IT. So the function phi sub t is defined on omega, not into the order. So here is omega is a reference value. And we consider some map. So usually you can understand that this map is just the flow of the fluid. So this at time t, omega is informed to omega sub t. Okay. omega sub t. So then the x, so for example, the x is usually we call it Euler coordinate. Then y is Lagrange coordinate. And then we are here. Usually we observe the flow is in Euler coordinate, so fixed coordinate. And then you ask when time t, you ask flow where you come from. Then the flow comes from here, omega. Right? So this is a correspondence of the Lagrange and the Euler coordinate. And then the equation is given in Euler coordinate. Equation is given in Euler coordinate. And I already gave this x is Euler coordinate. Then assume d smooth. When we derive the equations, then we assume that the phi sub t is a smooth function or map, smooth map. But when we solve the equation, then the phi sub t is some necessary smoothness. So it is a decide when we solve the equation how smooth the phi sub t is. But to derive the equations, we may assume that the phi sub t is smooth. Okay, then and also this is the injective map. Therefore, we have the inverse map. This is the inverse map. And we also assume it's not a function, but we consider usually this case the velocity field is given by dt by sub t y is here. This assumption, or usually we consider this case. So velocity field just so this is our flow, and then the velocity field is just by time derivative, and then position is now here. Position vector is now by the inverse. If we use the Euler coordinate, okay. So we here find. So here it is, x, therefore we consider the velocity field xt, but this xt is given in this way. But so this is our assumption or our situation. But for example, if you consider the phase transition. So, for example, here is water, and some gases, 100 degrees. And the water is going to be gases, and a little bit decrease in the temperature, then the gas is returned to water. So around 100 degrees is the fluid is really mixed gas and water, and the phase is transient. That case is maybe it's not. This is not satisfied. So phase transition case is different stories. So if I have a time, then maybe also this is a very interesting problem. Therefore, I would like to give you the formulation of equations, but maybe later. First, the most simplest case I treat. Anyway, so this is assumption, but if you consider the phase transition, then maybe this is different. Then now also the V, YT, Y. It's a Lagrangian, we call Lagrangian field. So Gxyt is also from the definition UPT. This is relationship. Just the definition. So now, therefore, what I want to say is that now we have two ways to observe the flow, viscous flow fluid. So one is the Lagrangian coordinate, the another is the Euler coordinate. Then this relationship, in important sense, is, for example, the example x equal y plus 2. Because x is the start from y. It's okay. X is counted here. Then velocity field is phi t. Okay, sorry, dt phi t. Therefore, just this x is equal to here y plus t to this. So just this representation is gives a relationship of x and y. So this is called Lagrangian transformation. Then important point is now that we consider the Jacobian of this transformation. Then I want to first proposition is the famous Reynolds transport theorem. This is the time derivative dtj give this is a famous theorem. So it is also the fundamental theorem for the mathematical fluid dynamics. Let's try to give a proof. Here is the important point is that now J is the variable for J is Y. There is. So then there is the divergence U equal the divergence X. Okay, anyway. Set. It's double Y. Then J this is the function. And we consider we have to consider the first approximation of this quantity with respect to delta t. Therefore, by value theorem. X y delta t is equal to t x y delta t square. Yeah. Oh, okay. So why? Yeah. I have to write. Okay, now y is fixed. So we consider only the time t. Therefore, this is usually I should write dtx, but you understand. Y is fixed. Therefore, under the yt is dx1 dy. One, two, sorry, not the matrix. And then notation is the coordinate is this way, 1 to n, and the differentiation is 1 to n. This is the rule of describing the matrix of gradient matrix. And then x prime yt is a time derivative. And it is just the xy dy1. Then determinant y is now determinant x. So again, I eliminate y. T plus t plus t. So then we multiply x inverse from right, and the determinant is a commutative, therefore that x plus that identity plus t plus t plus square. You can write in this way. Because determinant is commutative. That determinant A with AB is therefore you take you multiply x inverse here, and then xt and x inverse from left. But the determinant is and then now you calculate this determinant. So of course the I plus t xt inverse delta t. Okay, so plus blah blah square. But then it is just there is sorry, I forgot the English.対角線ってなんて言うんだっけ? Diagonal. So the diagonal here is so 1 plus d square x1 1 dt dyj, and then it's inverse, so dyj dx1 summation delta t. And then the diagonal second is 1 plus n d square x2 dt dyj dx2 delta t. And then another part is having here is delta t, something like that. Okay, so this is. And then how to only you one is okay. So you take the determinant of this. Then if you choose here, then you have to choose here. Therefore, off diagonal. If you choose off diagonal, then you get the delta t square. So therefore, in order to when you take a determinant, then only this is main part. The other part is you have delta t square. So
So you can write that I plus x prime t plus omega t squared. This is 1 plus dx j dyk x j delta t. I think yes. Yes, how to get the delta t is just only the first is 1, and then you multiply 1 plus, for example, 1 times this, or 1 times this, or this. Therefore, it's you have the just a trace. So here it is. And then, by chain rule, this is divergence 3t. So it's equal to divergence u. So for therefore, over delta t is equal to I minus u delta j t plus sorry. This is j. Take delta t to 0, and then you got the proposition. Okay, so you have a proposition. So this is a proof. Now, using this Reynolds transport theorem, I would like to drive equations. So, derivation. First, conservation of mass. It's okay. I mean, it's okay to the speed. Okay, so the conservation of mass is, of course, the d omega t is equal to 0. This is the conservation of mass. Then I want to use, because of the omega t is also changing according to the time. Therefore, use the Lagrange coordinate. Rho d. Okay. Lagrange coordinate. Then now you can put the d dt inside. So omega. So first you derivative term here, so dt rho. And then if derivative come to here, then it is Navier rho, not the chain rule, Navier rho and d phi d dt. Up to now is j plus the derivative come to here, so rho dtj. And then this is if you use that x coordinate, then this is u. Now I want to back from Lagrangian to Euler. Therefore, maybe representation is in x coordinate. dt rho plus xu j y. I'm sorry, I forget here. No here. And then by using the definition of divergence, this part you can write rho u. Divergence. The divergence is going to come here. This is Navier rho in a product u, and the divergence come here. Then rho times divergence u. Yes, okay. So this is, then you come back to the Euler coordinate. And then if you shrink omega t to the 1 point, then you get this is conservation of mass. Yeah, of course, there is some different way to write this equation, and more geometrical observations. But I like this. I prefer this more analytical observations. This conservation. Momentum. First, we consider the change of momentum with respect to time. So rho u x. So rho u, integration of rho u on omega t is the momentum. Rho u. So this is mass times velocity. It is momentum. Then we use the Lagrangian coordinate. Then the time derivative, you put time derivative into the inside of the integration. So this way. Then change ADT OJ J TQ. Then this is zero by conservation of mass. We already assumed that this is zero conservation of mass. Therefore, just only for this one. And this is the same calculation as before. I J du dt. So okay, now d. So u is really it. Therefore, time derivative here and also the derivation of the x variable. Therefore, x u. Now, so this is the how to drive the so-called material derivatives. So this is so we call the material derivatives. So the time derivatives plus velocity field dot nabla xu. So this is now we consider the flow velocity field, but if you consider any motion on some flow, then always you have some material A, B, D, T. If you consider any kind of motion on flow, then the time derivative of motion is not only motion. You get always you get this time material derivatives. So therefore, this is u. So So this is a derivative of momentum, time derivative of momentum. So the equation is usually time derivative of momentum is equal to forces. So internal force and external force F and F. External force. So this is a Newton law. But you know, maybe Daniel will maybe not very well because of you come from Pisa. But yeah, I forget. When a Newton drive, the famous story is the Newton drive this equation of momentum.
Okay. Newton used the geometry. Therefore, nobody can use Newton's law mathematically. And then Euler, I don't know, but Euler really find to describe the Newton's law by using the differential equations. So we use the Newton's law, and then we Navier-Stokes equations. But first mathematician who drive the equation describing the fluid motion is Euler. Euler used the Newton law. So almost the natural, if you know the Newton law, so this Euler equation is natural. But there is so Euler case is this is also give the pressure. So what Euler consider why do you have a fluid motion is artificial fluid particle you consider, and then fluid particle each other give some power, just force, it's pressure. Each fluid particle gives pressures. This caused the motion, fluid motion. Euler consider this way. So S is a very simple. And then of course the F is just external forces like gravity forces. Sorry. But I don't know the whole story is true or not. Someday, Navier look at the same river, some river. The fluid is smooth, viscous. Was here is slow motion, and after the bridge is much faster. So near the some obstacle, there's some distance. So you have to enter such effect in S. this is Navier sort of cost, but the Navier, maybe if you look to some books, then Navier, the definition of Navier is a complete nonsense. But anyway, Navier gave the Navier-Stokes equations. But after Navier, Stokes gave the correct way to derive the equations. This is, I don't know where, but someone told many years ago. And they also took some guaranteed book also wrote this thing. Maybe yes. So anyway, so I follow the Stokes. Stokes is very great mathematics. For example, even now vector analysis, if you give the lectures in the university, both undergraduate student, then you give one second process by university, then usually give Stokes theorem. It's very important. But and then also the books on calculus, the style is a Stokes style. Stokes gave a lecture note or some textbook, 19th century. Nothing changed. Still, we use Stokes. And then, of course, my calculator said it's a Japanese one. Originally, Stokes. So now we drive internal process. So another, for example, if you consider external process, gravity, but for example, also you can consider magnetic field. In this case, it's F is very much complicated. H is magnetic field. It's a magnetic coefficient. So if we consider the magnetic fluid, because you consider, for example, motion of the water, but also consider some magnetic effect, then you have to consider the most equations. In this case, F is given this way. As usual, I mean, I don't know how to drive it. And then H should satisfy some magnetic conditions. AB is a two-set product. In this case, I is 1 time. J is I is this is one kind of the equation for the magnetic field. So you have to consider two equations. Navier-Stokes and the equation for the magnetic field, and then the coupling. It's this magnetic field, and this is for the Stokes. So this is also external forces. If you consider the magnetic effect to the viscous fluid. This is no, I don't know. This not only this one, maybe different way to describe some of the effects from magnetic field. But this is very much low. How we consider the Q tensor. Q tensor also the same idea, but different. Q tensor is more complicated. It's crystal, so there is viscosity and align. Crystal is aligned. So for each point, alignment is in different directions. This is a big, it's a viscous fluid. There is some kind of crystal. Crystal was motion. Crystal described by just alignment. Yes. No, I don't want to give here the equation. It's pretty much complicated. But this is also some kind of example of the external forces. Anyway. So this is external forces. And then the internal. So usually we use the assumption Cauchy. Cauchy's consideration. This meaning is that individual is important for the country. Then how to describe this deformation? Usually we consider outer normal T. This outer normal is changed to here, and then this NT. This is an invariant matrix. So this is the formation. The formation of fluid particle is described by how change this unit normal vector of this T. So it is given by matrix S. This is Cauchy. Then this is E over T, S and T. Total change of unit vectors. This calls the internal energies and forces. So then by using the Gauss formulas, this gives S issue. The theorem of Gauss gives you the integration on the boundary is equal to the divergences, integration of divergences. If you remember the Euler equation, the equation of motion, momentum, it's given to Z. Equation of momentum. It's equal to, so just you take out this integration over T, then you have divergences, some divergence or something. This is the equation of momentum. The final part of the lecture today is what is this? This is the equation of momentum. Also, I hear my lecture. Use the Newton rule. Newtonian. I only consider that I never consider the non-Newtonian one. I only consider the Newtonian. So Newtonian law is the whole state that the S this is really information tensor. Okay, so usually W, how to explain? W is divide W symmetric part. Plus unsymmetric part. And this is deformation tensor. And this is the rotation tensor. This is rotation. This is deformation. Of course, if you solve this one,
And then if you consider this part, then you get just rotating motion. And here is deformation because, and then the fluid motion is don't get any stress from the rotation. Just get stress from deformation. Of course, deformation is this one. I mean, if you nabla you here, then nabla you this deformation is each particle. So deformation tensor is if you velocity field u, and then the gradient du dx1 x1 direction, x2 direction. So you have a deformation of a particle for each coordinate. And then so deformation is just symmetric before. So du it's gives you that the deformation of for each point. So usually the stress of the fluid get from this deformations because fluid shrinks and then they want to come back. So this is very much Newton considered in this way. Therefore, this is called Newtonian flow. But of course, there are a lot of nowadays we have a lot of non-Newtonian fluid. But mathematically, theoretically, Newton fluid is a very fundamental. Therefore, just consider Newton fluid. So this means that the S is linear with respect to du. So meaning it's Sij, SIS, the component of S is linear. Therefore, Aij plus Bij KL DKUL. This is assumption. Sij is a linear function of diu. Sorry, di. Sorry, dkl. Excuse me. So du L matrix. And then is double deformed tensor. Usually we write over 2, but okay, mathematics, therefore we don't need over 2. I mean, just double the deformation tensor. Consider. So Newton's law, Newton gave us the Sij given this way. And then now geometry. Then usually fluid observation of it's independent of choice of coordinate, Euler coordinate. So Sij, Aij, or DKL, Bijkl is for example, if you consider any rotation of coordinate translation, it's invariant. So under this, I don't know now. I don't. Maybe it takes a time if can. Okay, sorry. Under this under this assumption, Aij should be right scalar. Minus is maybe some constant. Some scalar times delta ij. Delta ij is symbols. Symbol. And Bijkl is given A delta ij delta kl plus E delta ik delta jl and C delta il delta jk. Observation. Now the fluid is independent of choice of coordinate, so-called frame indifference. Then Aij, this tensor Aij and Bijkl should written in this way. This is a tensor geometry. I'm sorry that I just believe it. I never use this one. Okay, therefore, Sij delta ij skl a this is right. Suppose it's minus p plus kl the same. I'm sorry. No. This is kl. Excuse me. Yes, here is. I'm sorry. I made a mistake. So first k and l equal same. Therefore, a no. This okay. dk and then second and third is I and K and J equal L. I and K. I equal K. Di L UJ IL DI so equal B plus C. Yeah, is this correct? Okay, so this is Sij. And then So the second momentum equation of momentum. Sorry, now the time almost over. So no. S is now minus P. Where is divergence? If you write a component wise, this ij is minus P delta ij plus A 1 to N pk uk ij B plus C di maybe so maybe this is ji. Otherwise, maybe J is symmetric. So this is much better. Oh no, TJ UI. Oh yes. Maybe this is correct. External forces. So therefore it's equal to this is divergence. So B plus C dj. I'm wrong. Oh, sorry, it's not. I'm wrong. This is right. So I and K equals same and J and L equals same dij. Yes. There is I and L equals same and J and K equals same, right? And then it's symmetry. Therefore, I'm sorry that this is correct. I'm wrong. So now this is correct. So here is, excuse me, Iju. Thank you. Sorry. So therefore, the equation A is equal to B plus C 1 to N Iju plus A, and it's divided dj di dv minus P di P. And then plus and then this is internal forces. Okay. It's okay. This is a derivation of internal forces. And then usually we write B plus C is equal to mu is the first, it's called Stephenson. And A is equal to mu minus mu. And this is the answer. Mu is equal to second the viscous constant. This is a derivation of the equation. And then, okay, now the time is over. I don't know, the last part, I don't know that good textbooks, last part, but then, for example, when I was young, I studied the whole, by using the whole master. Sorry, very old book because I studied this kind of things when I was young, almost 30 years ago. But then Japanese, so now Japanese. Japanese is 佐野先生の本がいいのかな。This is show cover. This is mechanics of the continuum field, something like that. The Japanese textbook. Anyway, it's like this. Okay. And both I found both books in Seikyo bookstore. But this I don't know. If you want to say that I borrow very old books. Okay, thank you very much. I stop here. Maybe next I maybe next I maybe introduce the boundary conditions, and then go to the theory.